This video is about the index of refraction. When we learned about Maxwell's equations, we saw that V was equal to the square root of 1 over epsilon naught times mu naught, which are the permittivity and the permeability of free space. Free space means a vacuum, and we saw when we plugged in the values for epsilon naught and mu naught, we got the speed of light. In air, the index of refraction is equal to 1.0003. Because if you round this to 4 significant figures, you get 1. In this class, aside from this video, we're going to pretend the index of refraction in air is 1. So when we talk about the wavelength in air, we really mean the wavelength in vacuum, but it doesn't matter because we're treating them both the same way. You have permittivity and permeability for different materials, which aren't really going to be important in this course, but what we were using for our constants in this course were those values in vacuum, but if you're in a material, you'd have a different permittivity and permeability. You can use those to find the index of refraction. You're not going to have to do that in this course because if you need the index of refraction, it will be given to you. But if you were interested in knowing the index of refraction for a certain material and you only knew its permittivity and permeability, you could find the index of refraction using this equation here. Okay, now if you're not in vacuum, the speed of light in that material is equal to 1 over the square root of epsilon times mu. So in a vacuum, it was the permittivity and permeability of free space, but in a different material, it would be the permittivity and permeability of that material. And if you look at this equation and this equation, you see that in some other material, the speed would be equal to the speed of light is equal to the speed of light in that material is equal to the speed of light in vacuum divided by the index of refraction for that material, which means that in other materials, light is going to travel slower. It can never go faster than it goes in vacuum, and it always goes the same speed in vacuum, but it will go at a slower speed in other materials, which means that the lowest possible value you can have for n is 1. So in vacuum, n is equal to 1. That's the smallest possible value you can get for the index of refraction, which means that the largest possible value you can get for the speed of light in a material is the speed of light. So the light can't go any faster than it goes in vacuum, which means the index of refraction can't be any smaller than 1. Okay, now I feel like we've seen this equation before, but I don't remember where we would have seen it. But if you take the wavelength and the frequency, you get the speed. So the frequency is hertz, which is 1 per second. The wavelength has units of meters, so that gives you units for speed. So the speed of light is also equal to the frequency times the wavelength. I guess we may have talked about this when we started electromagnetic waves because we said in vacuum the speed of light stays the same. So if the frequency increases, the wavelength must decrease because they have to multiply to give you the same speed. But now if you're talking about the speed of light in a material, the speed is going to change, but the frequency doesn't change. So the frequency stays the same, but the wavelength changes, which you might think is kind of unfortunate because that means when we're talking about the wavelength, you have to use this equation here because the wavelength in different materials is going to be different than what it was in air. Okay, so we can say in vacuum, the speed of light is equal to the frequency times the wavelength in vacuum. In a material, the speed of light is equal to the frequency times the wavelength of that material. So the frequency is the same in both cases. So I could take this equation and say the speed of light in a material is equal to c divided by the index of refraction for that material. So if I take this equation and divide it by the index of refraction, and then I say f is the same on both sides of the equation here, then we get this equation, which is almost the same as what I have here, except on the equation sheet I called it the wavelength for air, which I started to do there, but it's really vacuum. But then in this course it doesn't really matter because we're going to say 1.003 1.0003 is close enough to 1 that we aren't going to worry about it. Okay, so we're going to use this equation in this class, and that's really all we need to take away from the index of refraction.